We're gonna code a transformer from scratch. Hooray, StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about coding transformers from scratch in PyTorch. This StatQuest is brought to you by the letters A, B, and C. A always, B, C curious. Always be curious. I also want to use this opportunity to increase awareness of an awesome charity called GiveInternet.org, a platform that makes it simple and transparent for anyone to sponsor internet access, laptops, and education for underprivileged students. Note, the code in this StatQuest is available for free, so use the link in the pinned comment below to get your own copy and follow along. Lastly, in this StatQuest, we will be building a Decoder-Only transformer, which is the foundation for ChatGPT. Thus, if you are not already familiar with the concepts and matrix math behind Decoder-Only transformers, check out the quests. The first thing we do is import Torch to create the tensors we will use to store the raw data and to provide a few helper functions. Then we import torch.nn for the module, linear, and embedding classes and a bunch of other helper functions. Then we import torch.nn.functional to access the softmax function that we will use when calculating attention. Then we import atom to fit the neural network to the data with backpropagation. And to give us the tools to create a large-scale transformer network with lots of training data, we'll import tensor dataset and data loader from torch.utils.data. Lastly, we'll import Lightning as L to make it way easier to write our code and for automatic code optimization and scaling in the cloud. Bam! Now let's create the training dataset that we will use to train our transformer. For this example, all we want is for the transformer to respond to two different prompts. What is StatQuest? And StatQuest is what? And in both cases, we want the answer to be awesome. Thus, the vocabulary consists of the following tokens. What is StatQuest, awesome, and EOS? And we map the tokens to ID numbers because the PyTorch word embedding function that we will use, nn.embedding, only accepts numbers as input. And we save everything in a dictionary called token to ID. We then make a dictionary, ID to token, that can go from ID numbers back to the original tokens. These dictionaries will make it easy to format the input to the transformer and interpret the output from the transformer. Now let's talk about how to convert the prompts and the responses into a dataset. For example, if the prompt is, what is StatQuest? And the response is, awesome, then what will be the first input token? And ideally, since we want each token to generate what comes next, the first output token will be is. Then we want to use is as the next input token. And we want that to output StatQuest. Then we want StatQuest to output EOS to signify that we are done processing the input. So these three steps process the prompt. However, we're not yet done determining what the inputs and outputs should be for the transformer. Because we want the EOS token to output awesome, and we want awesome to generate a second EOS to indicate that we are done generating output. Thus, the tokens to use as input during training come from processing the prompt, as well as from generating the output. Likewise, the outputs that we use during training come from both stages. Thus, if these are our inputs for training, then we can code an input tensor using token to ID like this. What is StatQuest EOS awesome? Likewise, if the prompt is StatQuest is what, then we can code an input tensor using token to ID like this. StatQuest is what EOS awesome. Now, going back to the first prompt, what is StatQuest. When we generate the output from each decoder unit, is StatQuest EOS awesome EOS? We see we should code the label for the first prompt like this. Is StatQuest EOS awesome EOS? And we see we should code the label for the second prompt like this. Is what EOS awesome EOS? Ultimately, we have the input and label for the first prompt and response. What is StatQuest? Awesome. And the input and label for the second prompt and response. StatQuest is what? Awesome. And now we just pass inputs and labels to tensor dataset to create a tensor dataset object called dataset. And lastly, we pass dataset to data loader to create a data loader object called data loader. Bam! Now we know how to create the inputs and labels for the training dataset. The next part is word embedding. And we're just going to let nn.embedding take care of that for us. So, the next thing we need to talk about is position encoding. Position encoding commonly uses a sequence of alternating sine and cosine squiggles to calculate values for each token and embedding value. This is the equation for the first sine squiggle. Pos refers to the position or x-axis coordinate of the token in the input. This is the equation for the first cosine squiggle. This is the equation for the second sine squiggle. The 2 indicates that this is the second sine squiggle. And D model refers to the number of values we are using per token. This is the equation for the second cosine squiggle. In general, these are the equations we can use for as many tokens as we want, with each token specified with pos, and each embedding position specified with I. Note, this +1 simply means that the cosine comes after the sine, and doesn't change the formula within the cosine function. In other words, the formula inside the sine function is identical to the formula inside the cosine function. Now let's work through an example so that we can see these equations in action. If we had 2 tokens, then for the first token, pos equals 0. And for the second token, pos equals 1. Now, if each token had 4 word embeddings, then D model equals 4. Then, for the first token, we calculate the position encoding values by starting with I equals 0. So we plug pos equals 0 and I equals 0 into the 2 equations. We'll start with the sine function. Bip, 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 boo. And we get 0. So 0 is the first position encoding value. Now let's evaluate the cosine function. Ba-bing. And we get 1. So 1 is the second position encoding value. Now, because we still have 2 more word embedding values to add positional encoding to, we increment I, the word embedding index, by 1. And then plug pos equals 0 and I equals 1 into the sine function, and 0 is the third position encoding value. Then we plug pos equals 0 and I equals 1 into the cosine function, and 1 is the fourth position encoding value. So I equals 0 is used for the first 2 position encoding values, since we have 2 functions, sine and cosine. And I equals 1 is used for the second 2 position encoding values. For the next token, we increment pos by 1, and reset I so that I equals 0. And then calculate the first 2 position encoding values just like before. Bam! Now that we have the first 2 position encoding values for the second token, we increment I by 1, and then calculate the second 2 position encoding values. Beep, boop, beep, boop, boop, beep, beep, boop, boop, beep, beep, boop. Bam! Anyway, rather than use these equations each time we want to add positional encoding to a token, we pre-compute the y-axis values and store them in a matrix. This makes adding position encoding values super fast. Here's the code that we'll use to pre-compute and add position encoding values to the tokens. We start by defining a new class, position encoding, that inherits from nn.module. Then, like always, we define an init method. dModel, which is short for dimension of the model, is the number of word embedding values per token. And maxlen is the maximum number of tokens our transformer can process, input and output combined. Note, for this super simple example, we're setting dModel to 2 and maxlen to 6, but in practice, you would set them to much larger values. Then we call nn.module's init method. And now we start the code that will create a matrix of position encoding values. We start by creating a matrix that we call PE for position encodings that is full of zeros. PE will have maxlen rows and dModel columns. For example, if maxlen equals 3 and dModel equals 2, PE will start out looking like this. Now we create a column matrix, position, that represents the positions, pos, for each token. We're using torch.arange to create a sequence of numbers between 0 and maxlen. And .float ensures that the numbers are floats. And .unsqueeze1 turns the sequence of numbers into a column matrix. For example, if maxlen equals 3, then we will get this column matrix. Now we create a row matrix, embedding position, that represents the index, I, times 2 for each word embedding. Just like before, we use torch.arange to create a sequence of numbers, but this time they are between 0 and dModel. Note, setting step equals to 2 results in the same sequence of numbers that we would get if we multiplied I by 2. So, by setting step equal to 2, we save ourselves a little math. And, just like before, we use .float to ensure that the numbers are floats. Thus, when dModel equals 2, then embedding index is just a single value, 0. But when dModel equals 6, then we end up with 3 values. Now, each value in position is divided by this term. So we create div term to represent the divisor. Now we just do the math. The first line assigns values from the sign function to the matrix PE, starting with the first column, column 0, and then this 2 means every other column after that. The second line assigns values from the cosine function to the matrix PE, starting with the second column, column 1, and then this 2 means every other column after that. Ultimately, if we use the default values, maxlen equals 3 and dModels equals 2, PE will end up looking like this, where the first column has values from the sine function, and the second column has values from the cosine function. Lastly, we use register buffer to ensure that PE gets moved to a GPU if we use one. Now we create a forward method that takes in word embedding values and adds the position encoding values to the word embedding values. And that's all we have to do to code positional encoding. Bam! Now that we have the position encoding taken care of, let's talk about masked self-attention. The first thing we need to do is calculate the query, key, and values for each token. And that means we need to code all of this math. And in PyTorch, that means we need to use matrix notation. For example, if we have the word embeddings plus position encoding values for what, is, and EOS, then we can do all of the math required to create query values, the multiplication by these weights, and the summations by multiplying the encoded values for the tokens by a matrix that contains the weights associated with creating the queries. That matrix multiplication will give us a matrix of query values that we'll call Q that has one row per encoded token. Likewise, we can multiply the encoded tokens by a matrix containing the weights associated with creating key values to create a matrix called K that contains key values for each token. Lastly, we can multiply the encoded tokens by a matrix containing the weights associated with creating value numbers to create a matrix of values that we will call V. Thus, when we code an attention class in PyTorch, we replace this tree-like diagram with matrix multiplication that creates the queries, keys, and values. So we start by defining a class called attention that inherits from init.module. Then, just like always, we create an init method. In this case, we're passing the init method dModel, the dimension of the model, or the number of word embedding values per token. We need to know the number of word embedding values per token because that defines how large the weight matrices are that we use to create the queries, keys, and values. In this specific example, we're using 2 word embedding values for each token, so dModel equals 2. And that means each weight matrix needs dModel equal to 2 rows and dModel equal to 2 columns, so that we end up with dModel equals to 2 query numbers per token. Bam! The next thing we do is call the parent's init method. Now, in order to create the weight matrix that we will use to calculate the query values, Q, we will use nn.linear, which will create the weight matrix and do the math for us. N features defines how many rows are in the weight matrix, so we set it to dModel. And out features defines the number of columns in the weight matrix, so we set it to dModel as well. Lastly, in the original Transformers manuscript, they don't add additional bias terms when calculating attention, so we won't either by setting bias equal to false. As a result, we end up with an object we're calling WQ, with the currently untrained weights needed to calculate query values. And because WQ is a linear object, it doesn't just store the weights, but it'll also do the math for us when the time comes. Then we do the exact same thing to create a linear object, WK, that contains the weights needed to calculate the keys. Lastly, we create a linear object, WV, to calculate the values. And just to give us flexibility to input training data in sequentially or in batches, we create some variables to keep track of which indices are for rows and columns. The forward method is where we actually calculate the masked self-attention values for each token. And another thing we're doing for the sake of flexibility is allowing the query, key, and values to be calculated from different token encodings. For example, encoder-decoder transformers have something called encoder-decoder attention, where the keys and values are calculated from the encoded tokens in the encoder, and the queries are calculated from the encoded tokens in the decoder. So, allowing the encodings to come from different sources gives us the flexibility to do encoder-decoder attention if we want to. Also, since we want to be able to do masked self-attention, we can pass in a mask. Now we calculate the query, key, and values for each token by passing the encodings to each linear object. And now we are ready to calculate attention. We start by using torch.matmul to multiply Q by the transpose of K. This calculates the similarities between the queries and the keys, which we save in sims. Then we scale the similarities by the square root of the number of values used in each key. Note, this scaling is something that has been standard practice since the original Transformer manuscript in 2017. However, it's not required and really only helps out when the model is relatively large. The next thing we do is add the mask, if we're using one, to the scaled similarities. Masking is used to prevent early tokens from cheating and looking ahead at later tokens. To understand how we add a mask using the masked fill method, Let's imagine that the mask is a matrix of trues and falses. And the trues correspond to attention values that we want to ignore. So the masked fill method replaces the trues with -1 times 10 to the ninth, which represents -1 billion, an approximation of negative infinity. And it replaces the falses with 0 to create the final mask that is added to the scaled similarities in scaled sims. The next thing we do to calculate attention is run the scaled similarities through a softmax function. Applying the softmax function to the scaled similarities determines the percentages of influence that each token should have on the others, which is why we store the results in a variable called attention percents. Lastly, we use torch.matmul to multiply the attention percentages by the values in V. And that gives us the final attention scores stored in attention scores, which we return. Bam! And now that we have coded the attention class, we can create a class that puts the first 3 steps together, and then adds the residual connections, and then runs those values through a fully connected layer, and then runs them through a softmax to get the outputs. And we do that by creating a class called Decoder-Only transformer. Note, unlike the position encoding and attention classes we created earlier, this one inherits from Lightning module. Doing it this way, rather than having every class inherit from Lightning module, allows us to take advantage of everything Lightning offers without the overhead of inheriting it multiple times. Anyway, first we create the init method, which allows us to specify num tokens, the number of tokens in the vocabulary. Dmodel, the number of values we want to represent each token, and maxlen, the maximum length of the input plus output. Then, as always, we call the parent's init method. Then we create an embedding object and we name it WE for word embedding. Embedding needs to know how many tokens are in the vocabulary and the number of values we want to represent each token. Then we create a position encoding object using the class we created earlier and name it PE. And then we create an attention object. Then we create the fully connected layer with nn.linear. nn.linear needs to know how many inputs there are and how many outputs there are. Then we create the loss function to quantify how well the model performs. In this case, we're using cross-entropy loss, because our model has multiple outputs. And cross-entropy loss will apply the softmax function for us. Now we put all the pieces together in the forward method. Forward takes an array of token ID numbers that will be used as inputs to the transformer. First, we convert the tokens into word embedding values. Then we add the position encoding. And then we create the mask that will prevent early tokens from looking at late tokens when we calculate attention. We start by creating a matrix of ones with torch.ones. For example, if we pass 4 token IDs into this method, then the call to torch.ones will make a matrix with 4 rows and 4 columns full of ones. That matrix of ones is then passed to torch.try_L. And I believe that try_L is pronounced try_L, where L stands for lower triangle, because torch.try_L leaves the values in the lower triangle as they are and turns everything else into zeros. Ultimately, we save a matrix with ones in the lower triangle and zeros in the upper triangle in a variable called mask. Then we use mask == 0 to convert the zeros into trues and the ones into falses. And, in the end, if we pass in 4 token IDs, this is the mask we will use for masked self-attention. Once we have the mask, we calculate attention. Note, because the query, key, and value matrices will all be calculated from the same token encodings, we pass in the same set of position-encoded values 3 times for the queries, keys, and values. We also pass in the mask so that early tokens can't cheat and look ahead at later tokens. And then we add the residual connections. And lastly, run everything through a fully connected layer. Remember, the loss function we are using, cross-entropy loss, does the softmax for us. So all we have to do is return the output from the fully connected layer. Bam! Now that we have coded a decoder-only transformer, we need to write the code required to train it. So the next thing we do is create a method to configure the optimizer we're using. In this case, we're using Atom, which is like stochastic gradient descent, but a little less stochastic. And we're passing all the weights and biases in the model that we want to train, which is all of them, to Atom. And in this example, we're setting the learning rate to 0.1 because it makes training this specific model very fast. However, the default value, 0.001, is probably more commonly used. Then we code a training step method, which takes a batch of training data and an index for that batch. We then split the training data into inputs and labels, and then pass the input tokens into the forward method that we just wrote to compute the output. And then we compare the output from the transformer to the known labels using the loss function. And remember, the loss function does the softmax for us. Lastly, we return the loss. Bam! Now let's run the model before training it, just to see what it does. So, the first thing we do is create a model from the decoder-only transformer class that we just created. Then we create an input prompt. In this case, we're using what is StatQuest EOS. Then we figure out how many tokens we are using as input. We do this because our super simple model can only handle a total of 6 tokens. So, keeping track of how many tokens are in the input will tell us how many we can create as output. Then we run that through the transformer, which generates predictions for each token in the input. This means that the model generates a prediction for what should come after the first token, what, and for all of the other input tokens. However, we're really just interested in what the model predicts will come after the EOS token. So we use -1 to index the outputs generated by the EOS token. The outputs generated by the EOS token are an array of output values, one per possible output token. So we use the argmax function to identify the output token with the largest value. Thus, the token with the largest output value will be the first token generated as a response to the input. Note, we don't have to take the token with the largest value if we don't want, and this is something that is often configured in more complicated models. Anyway, we save that token so that we can print it out later. Then we use a loop to keep generating output tokens until we reach the maximum number of tokens that our model can generate, or the model generates the EOS token. Note, each time we generate a new output token, we add it to the input so that each prediction is made with the full context. And then the model predicts the next output token using the full context, which is the input plus the output tokens so far. Lastly, we print out the generated tokens after converting them from ID numbers to text. Now, when we run this code, the response to the input, what is StatQuest EOS, is EOS. And that is not what we wanted. Ideally, we would have gotten awesome EOS. So that means we need to train the model. The good news is that the code for training is super simple. First, we create a lightning trainer and tell it to only do 30 epochs, which is enough for our simple model and dataset. And then we pass our model and the data loader we created earlier to the trainer using the fit method. And after we train the model, we rerun the code we wrote earlier that generates a response to the prompt, what is StatQuest EOS? However, this time we don't create a new model at the start. We use the one that we just trained. Anyway, the output is awesome, EOS. Bam! Now let's see what happens when the input prompt is StatQuest is what, EOS. Using the same code we used earlier, and the output is awesome, EOS. And that means our decoder-only transformer works exactly as expected. Triple bam! Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out the StatQuest PDF study guides and my book, The StatQuest Illustrated Guide to Machine Learning, at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying one or two of my original songs, or a t-shirt or a hoodie, or just donate. The links are in the description below. All right, until next time, Quest on!